Hey guys, welcome to part 2 of this video series. In this video, I'm going to be going over a challenge buffer problem, a introduction on selecting indicators and buffer solutions, as well as an introduction on titrations and a couple of titration problems. So let's get started. If I need a solution with a pH of 4.2 and I have a 1 liter solution containing a concentration of 1 molar acetic acid and a 0.01 molar concentration of sodium acetate, how much sodium hydroxide would I add to my solution to get my desired pH? Well, first things first, let's write out the Henderson-Housebach equation, which says pH is equal to your pKa plus the log of your conjugate base over your acid. All right, so far so good. And we're trying to solve for the pH, so let's plug that in. 4.2 is equal to our pKa, which is 4.74, plus the log of x, because I'm not going to put in 0.1 over 1, because this is a variable that's going to be manipulated by the sodium hydroxide. So when we solve for log of x, we're going to get log of x is equal to minus 0.54, and so the inverse of a log is to raise to base 10, so 10 to the minus 0.54 is equal to x, which is equal to 0.2884. So what does this 0.2884 represent? Well, this 0.2884 represents the second part of the argument. It represents the ratio of base to acid we have to get to. Well, that doesn't really tell us much if we don't know what happens when we add sodium hydroxide. So what happens when we add sodium hydroxide is, since it's a base, it's going to react with the most acidic portion of the solution, which is the acetic acid. So it's going to go to the acetic acid, and this acetic acid is then going to convert into sodium acetate, because that's how buffer solutions work, and it's going to interconvert between that. So the way we'd represent this as an equation is as it would be that we're gaining base and losing acid. So we could do that. We could represent this as 1 minus x, because the amount of sodium hydroxide we add is proportional to the amount of acetic acid we lose, which converts to sodium acetate. So, and then when we solve this, when we put this in, we can solve for our x pretty simply just by multiplying out. And you should get x being equal to 0.22, and then you can plug and check, and that should get you your answer. So when I made this problem, I didn't expect it to be that difficult, but I had to go through it step by step to realize that it did require some unique work. So if you understand this problem, then you probably have a good understanding of the or a good algebraic understanding of the Henderson-Housebach equation. So moving on, what acid would I use, or what combination of acids and bases would I use if I wanted a solution with a pH around 4.2? And this denotes our Ka. Well, first things first, I'll give you guys a couple seconds to solve. All right, there we go. Well, if this is the Ka, the negative log has to be, you want it around 4.2. And if you don't understand why, let's write out, if we can recall the Henderson-Housebach equation, it says our pKa plus our log of our conjugate base of our acid. So the pKa is going to be the axis around which the pH is manipulated around. So you want something that's going to be manipulated around 4.2. So really anything around here would be a good answer, but the best answer would be benzoic acid and the hydrogen oxalate ion. So moving on to indicators. So indicators function in a similar manner. So indicators are a chemical species that undergoes a anatomical change, or a change in the structure of the molecule under certain pH conditions, which can be observed by us. So let's think about that. So each indicator has a pH range in which they function in, and this corresponds to the pKa. So here's a list of indicators as well as the pKa that each indicator has. And the most common one we use is phenolphthalein, or phenolphthalein, which is an indicator that has a equivalence point near 7, and that has a pH range around 8 to 10, and which, when you do basic titrations of sodium hydroxide and HCl, you'll see it turn purple when it gets slightly basic, and then turn very dark red when it's very acidic. So you probably have never seen it turn that ominous red color, but it can turn red. And that's because of the change in the structure during that pH range. So let's move on to titrations. And titrations are supposedly the most difficult part of this of the acid-base section, or so what general chemistry students told me. And I think the real reason why titrations were difficult to students last year is because they didn't have the groundwork. I feel like a lot of people, if you get caught up in the if you don't have the groundwork, then you can't build up your structure, is my understanding, is how I've always viewed titration. So let's go through this step by step, and I think coming out of this, you guys will get a better understanding of titrations. So let's begin. So the definition of titration is adding a titrant of a known concentration incrementally to a solution of unknown concentration until the solution reaches an endpoint. Well, what's a titrant? Well, a titrant is the reagent solution added to the analyte incrementally through precise volumetric glassware such as burette. Well, a burette, as we know, is a piece of glassware that we can measure very precisely. But what's an analyte? I suppose I'm trying to go through step by step. Sorry if this is tedious, but I think you really have to understand everything. Well, an analyte's the substance you're trying to identify. So I think so. If we can just backtrack a little bit, it's the reagent solution we add can help us solve our analyte. So I guess in some sense you're using a known solution to find an unknown concentration is the dumbed down version of it. So I think this would be a lot more better understood if I went through this with a list of terms and how they correspond to the physical representation by titration and the pH graphs of the titration. So analyte is a species you're trying to measure, your unknown concentration. And that is what you're going to find out. A titration is a procedure, as shown here. You have which is shown by having a acid or base solution, then adding an indicator, and then adding a titrant to find your analyte, which corresponds to the change in your solution, which the indicator represents. The indicator changes at that point. So what is a blank titration? And so this is a little difficult to understand, so I'll come back to this one. I'll come back to that. And I'll come back to primary standard as well. Let me go to equivalence point. So an equivalence point is when you have your equal molar concentration of base and acid added to one another. So in theory, the equivalence point of a strong acid should be 7. The endpoint is where you notice a physical change in your solution. So this is where your indicator would change. And the difference between these two, because the indicator always occurs, usually occurs a little later. So the indicator, let's say, occurs at a pH of 10. Or actually, when I did this in analytical chemistry, it was around 9.3, if I recall exactly. That was a jaded 3. 9.3. The difference between the equivalence point and endpoint, which the endpoint is where your indicator changes, is known as your titration error. And the way you correct your titration error is by doing a blank titration. So what a blank titration is where you have a concentration of a usually distilled water, and you add an indicator, and then you add your titrant, let's say your acid, or let's say in this case, you added sodium hydroxide to this distilled water. And the amount of sodium hydroxide you had to add to notice an observable change in this indicator would represent your sort of your shift. So I'm going to pause the video and come back to this and show you what I mean in a more a better understood way, or graphical way, I suppose. All right, so here's the graphic I made. It's a little, I know it's not the best, but I think this will help. So let's say the amount of milliliters you add correspond to the x-axis. And let's say this is how much sample you added before you notice something in your endpoint or your indicator changing. And so then you run a blank to see how much you had to add to notice something on your indicator, the blank on water. And you can subtract that from your sample. Whoops. You can subtract that from your samples to get your equivalence point. But of course, there's always going to be errors associated with this. So what is a primary standard? Well, a primary standard is what you weigh out, and the exact definitional term would be something with a known concentration and a known mass. So usually the primary standard you use is something like, how do I put this? Usually when you're selecting something for a primary standard, there's usually properties to this. So for the most commonly used primary standard that I know of would be, like, for example, measuring out KHP and then using that to standardize your sodium hydroxide. And KHP is a weak acid, and usually the thing you standardize with has properties such as a large weak acid, and then you titrate that with your strong base. And those are, and I forget exactly why, so someone could research that and email me. That'd actually be pretty nice. Standardization is the process by titrating a titrant of unknown concentration against a solution of a known reference acid or base. So sort of similar to what the idea of titrating in general. So moving on to an example of a titration calculation. So this was originally going to be in my recitation, but things never came to be. So an example of a 50 ml solution of 0.1 molar HCl is titrated with 25 mils of 0.5 molar sodium hydroxide. Calculate the pH at 0, 5, 7.5, 9.8, 9.99, 10 mils, 12.25, 15 mils, 20 mils, and 25 mils. Well, I never got to edit this portion of the slides exactly. So let me write out how you calculate these, then I'll go through it step by step. Actually, I can just show you here. Pause. All right, I'm back. So I just wrote out how you'd solve these problems. And so initially this was 0.2 molar. I forget why I changed. I think because there might have been a problem in very similar to in your homework, and so I thought it might have been a little redundant to do so. But I'll do the initial calculations with 0.5 molar, and then I can come back and show you how to solve these. So for 0 mils, pretty simple to solve. You just take the negative log of 0.1 molar because that's the concentration of your acid. And then for the rest of these, you do something a little different. So you have to subtract your moles, not your molarity, of sodium hydroxide from your HCl, and then convert it to molarity to get your pH. So what I mean by that? So let's start off from the very beginning. So 50 milliliters is 0.05 liters times 0.1 molar HCl minus 0.005 milliliters, so 0.005 liters of sodium hydroxide times 0.5 molar. And then you're going to divide by the total volume in that, because the amount of moles divided by volume is your molarity. So, and you take the negative log of that. And if you take your negative log of that whole expression, you get 2.60206. And so this is the same idea for concentrate. This is the general idea of how you do pH calculations for anything under. And I actually have an Excel sheet that I'm going to email out, and then you can look at it to see how you solve these kinds of problems. Because I think if you look at the Excel sheet, it'll elucidate this a little bit better, because you can see the numerical approach if you're analytical in that kind of sense like me. So let's do another one. So with 7.5 milliliters added, same thing. You're assuming that this neutralizes the HCl because you have excess HCl up until you reach your equivalence point, which in this case would be, if I'm using 0.5 molar, you'd have to set up an expression, but that'd be about, around 10 mils. So yeah, this is actually still correct, not 0.2 mils. So you would you do the same thing. You subtract it because you assume it neutralizes it. Then you divide by the total volume, which is 0.0575 liters, to get your molarity. Then you take the negative log of that, and you should get your solution to be 2.9039. So for the first three, and then the rest aren't going to be on the Excel sheet I email out. And actually, you can look at it here. The Excel sheet glitches because you can't take the log of a 0, but at that point is when pH equals POH, which equals 7. So when you add excess sodium hydroxide, you can see how the POH changes, and it should correspond to be the same kind of numbers if I incremented it right. Yep, and you can see that there, which isn't your pH because that's your POH. So this is, in my opinion, the problem I don't like. I don't like these kinds of problems. I'm gonna be upfront with you guys. A titration problem with a weak acid and a strong base. So I believe in you guys. I know you guys can do this, but these problems are a little tedious. So let's say I have 45 mils of 0.2 molar acetic acid and 40 mils of 0.1 molar sodium hydroxide. What is the pH? Assuming acetic acid has a pKa of Ka of 1.8 times 10 to the minus 5. So I'm gonna take a second to pause and then come back to this. All right, I'm back. So let's go back to this problem. Let's start from the very beginning. So let's say I have 45 mils of 0.2 molar acetic acid and 40 mils of 0.1 molar sodium hydroxide. So first thing you're going to do is you're going to convert these to moles. That's the very first step. And so you're going to convert the 45 mils to 0.045 liters times 0.2 molar. Now, I know it's not the best unit analysis, but this is just the average form to make it a little quicker for you guys. So it's going to be 0.09 moles of acetic acid, and then you're going to have 0.004 moles of base when you multiply it all out, because you have 0.04 times 0.1. Now, what's going to happen is this base is going to react with the acid, and it's going to make 0.005 mole of acid and 0.004 mole of base. So let's go back and think about our basics. So we're going to have 0.004 mole of base because it reacts, converts to base, and then this acid is what's remained. So we can plug this into our equilibrium expression and create a rice table for this. But before we do that, we have to get our molarity, because we just have moles, not our molarity. And the total volume is going to be 85 mils. So we have to solve for our molarity. So for acetic acid, I'm just going to pause it right now and write it out real quick. But yeah, since we have 85 milliliters, you divide 85 by 1,000, so you get 0.085 liters. So you can solve for molarity, and we get 0.0588 molar acid. So 0.0588 is the molarity of the acid, and 0.047 is the molarity of the base when you carry out the same procedure for the base. So I'm gonna, oh, whoops, this pen's a little hard to get used to. So I'm gonna erase all this and then show you how you'd plug this into your rice table, and then we should be good from there. But this is the reason I don't like these kinds of problems, because there's just a lot of work. So I'm gonna pause it for a second and then come right back. All right, I'm back. So I set up the rice table, and what you're gonna end up getting is 0.0588 for your initial, and then since you're starting off with the initial, you're gonna lose a concentration, so mine's 6. Uh, and since you have more acetic acid than base. Uh, and then when you set it up, it's sort of redundant because you set this all up, but you don't actually have to, because the x is so small in the end of the day that you can just do x times 0.047 divided by 0.0588, which is your initial concentration, your reactant, and then over your product, which is your base. And I know that might seem a little confusing, but if you look at the rice table, then you look at the Ka as you set it up properly, is what you're going to get. And really, it should be 0.047 plus x over 0.058 minus x. But when you do it and you solve it, it doesn't make that much of a difference. It just ends up being more complex math, and you get about the same answer. So you can sort of use a shortcut here. And actually, I believe the homework does a shortcut, does a problem with a smaller Ka, meaning this is more significant, and they still use a shortcut. And you should get x being equal to 2.25 times 10 to the minus fifth, and then you take the negative log of x, and you should get your pH to be, because that's how you solve for your pH, because that's your concentration, your H plus, to be 4.64. And that should be it for this recitation. So thank you, and email me if you have any questions or suggestions. That suggestions are always appreciated. And actually, email me if you watch this. That'd be really nice, so I get an idea of how many people stuck through it. Hope you guys have a good one. Take care. See ya.